In March 2026, a researcher stood up at the Lunar and Planetary Science Conference in Texas and showed the room something that, according to the basic physics, every planetary scientist in that audience had studied for their entire career, should not be able to exist. An asteroid, nearly the size of 8 football fields, spinning completely around once every 112 seconds. Not once an hour, not once every few minutes. Once every 112 seconds, fast enough that any loose rubble pile of that size should have torn itself apart from centrifugal force alone. The session chair's response, on the record, was a simple question nobody in the room could actually answer. How does that get created? Everybody, this is the real story of what the Vera Rubin Observatory found in its very first test images, before its actual 10-year survey had even officially begun. And it's a genuinely strange discovery that's still sitting unexplained in the scientific literature right now. Let's start with the telescope itself, because understanding what makes Rubin different from every other observatory currently operating is essential to understanding why it found something like this almost by accident. The Vera Rubin Observatory sits on Cerro Pachon in Chile, jointly funded by the National Science Foundation and the Department of Energy, and it's built around two things. Nothing else in astronomy currently combines at this scale. An 4-meter mirror paired with the largest digital camera ever constructed for astronomy, a 3,200 megapixel instrument called the LSST camera, LSST standing for Legacy Survey of Space and Time. Rubin's entire mission, once its official 10-year survey begins, is to photograph the visible southern sky in its entirety every few nights, building a continuous, time-lapse record of literally everything that changes. Asteroids drifting past, stars exploding, galaxies flaring over and over for a full decade. It's less a telescope in the traditional sense, and more a dedicated change detection machine for the entire sky. Even before that official 10-year survey formally began, Rubin's engineering and commissioning teams ran a series of test observations to make sure the camera and software pipeline actually worked as intended. In June 2025, during what the observatory called its first look event, Rubin released a set of images captured while repeatedly photographing the region around the Virgo cluster between April and May of that year. Buried inside that test data set, meant purely as an engineering check, the telescope had already recorded roughly 1,900 previously unknown asteroids drifting through our own solar system, an almost absurd volume of new discoveries from what was technically just a systems test, not even the real survey yet. That's when Sarah Greenstreet, an assistant astronomer at NSF Noir Lab and the lead of Rubin's Solar System Science Collaboration Working Group focused specifically on near-Earth objects and interstellar objects, led a team digging through that same test data looking for something specific, asteroids that rotated unusually fast. What they found, published in January 2026 in the Astrophysical Journal Letters, was a set of 19 super and ultra-fast rotating asteroids hiding inside that engineering dataset. 18 of them sat in the main asteroid belt, the region between Mars and Jupiter, where most of the solar system's rocky debris orbits, a location that makes fast rotators considerably harder to find in the first place, since anything that far from Earth is fainter and more difficult to track precisely than the near-Earth objects astronomers usually study for this kind of behavior. And then there was one asteroid that stood out from even that unusual group. Designated a 2025 MN45, this object measures 710 meters across, roughly 44 miles, comparable in scale to nearly 8 football fields laid end to end, or almost twice the height of the Empire State Building if you stood it on end. And it completes one full rotation every 88 minutes. That makes it, officially, the fastest rotating asteroid larger than 500 meters in diameter that scientists have ever recorded, anywhere, at any point in the history of asteroid observation. If a real, still unexplained mystery like this, caught almost by accident during a routine equipment test, is exactly the kind of space science you come here for, subscribe now. Because the reason this specific discovery has planetary scientists genuinely stumped goes deeper than just the raw speed record itself. Because here's the actual physics problem sitting underneath this discovery, and it's worth understanding clearly, because it's the entire reason this isn't just a novelty statistic. Most asteroids larger than roughly 150 meters across aren't solid single chunks of rock at all. They're what scientists call rubble piles, loosely bound collections of smaller rocks and gravel, held together almost entirely by their own weak mutual gravity rather than any real structural strength, similar in some ways to a pile of sand or gravel drifting through space rather than a solid boulder. Because that gravitational binding is so weak, there's a well-established physical limit on how fast an object like that can spin before it simply flies apart. Centrifugal force at the object's equator, overwhelming the feeble gravity trying to hold the loose material together. Scientists call this the spin barrier. And for a rubble pile asteroid larger than about 150 meters, that barrier generally sits somewhere around a rotation period of 2 hours. Spin faster than that, and a loosely bound rubble pile should tear itself apart, flinging debris outward until it either breaks into smaller pieces or reshapes itself into something stable at a slower rotation rate. 2025. NN45 isn't spinning close to that 2-hour limit. It's spinning at 88 minutes, dramatically faster than the threshold at which any loosely bound rubble pile of its size should be able to hold together at all. Dmitry Vavilov, a researcher at the University of Washington who presented these findings at the Lunar and Planetary Science Conference, put the implication plainly. He said the asteroid is spinning at a rate very close to the actual physical strength limit for solid, unfractured rock. Essentially the absolute upper boundary for how fast any object of that size could rotate without flying apart, regardless of what it's made of. Vavilov went further, stating directly that the asteroid is probably one big, solid piece of rock, or possibly even metal, rather than the loose rubble pile structure most asteroids this size are assumed to have. He summarized the situation with a line that captures exactly why this discovery genuinely unsettled the room it was presented to. He said plainly that objects like this are not supposed to rotate that fast, and yet it does. That reaction wasn't limited to the researcher presenting the findings. Casey Lisa, from the Johns Hopkins University Applied Physics Laboratory, was chairing the session where Vavilov presented these results, and his own on-the-record response, asking simply how something like this could have been created in the first place, reflects genuine unresolved confusion from an established expert in the field, not manufactured drama for a headline. When a session chair at a professional planetary science conference publicly asks a presenting researcher how their own discovery is even physically possible, that's about as clear a signal as you'll ever get that a result has genuinely broken the existing model, rather than simply extending it. So what's the actual explanation? Right now, honestly, there isn't a fully confirmed one, and that's worth sitting with rather than rushing past. The leading working hypothesis is the one Vavilov himself proposed, that 2025 MN45 isn't a rubble pile at all, but a genuinely solid, coherent chunk of rock or metal, the kind of object that doesn't have the same weak internal binding a loose rubble pile does, and therefore isn't subject to the same 2-hour spin barrier that limits most asteroids of comparable size. If that's correct, it would mean 2025 NN45 represents a genuinely rare category of large asteroid, a solid monolithic body rather than the loosely aggregated rubble most objects its size turn out to be once studied closely. But confirming that explanation definitively would require considerably more detailed study of the object's composition and internal structure than a rotation period measurement alone can provide, the kind of follow-up observation that becomes possible once Rubin's full 10-year survey is underway and can revisit this specific object repeatedly over time. There's a broader reason this particular discovery matters beyond the fate of one unusual rock, and it connects directly to why Rubin was built in the first place. Most fast-rotating asteroids discovered before Rubin came online were near-Earth objects, meaning they orbit relatively close to our own planet, making them brighter, easier to spot, and easier to study in detail. Main belt asteroids, sitting much farther away between Mars and Jupiter, are considerably fainter and harder to characterize, which is exactly why astronomers had found comparatively few fast rotators out in that more distant region before now. Rubin's fundamental advantage, according to the observatory's own team, comes down to raw light collecting power combined with extremely precise measurement capability, allowing it to track subtle brightness variations in objects far fainter and more distant than most existing asteroid surveys can reliably detect. That's precisely why 18 of the 19 fast rotators in this dataset turned up in the main belt rather than closer to Earth, a direct demonstration that Rubin is now finding this kind of extreme physics-testing object at distances that were previously simply too faint to properly study. Aaron Rudman, deputy head of Rubin's Legacy Survey of Space and Time and a professor of particle physics and astrophysics at SLAC National Accelerator Laboratory, framed the broader significance of this entire dataset directly. He said the observatory has known for years that Rubin would function as a genuine discovery machine for the universe, and that the team is already witnessing the unique power of combining the LSST camera with Rubin's remarkable observing speed. He pointed out that finding thousands of new asteroids in such a short period of time and learning this much detail about them offers a real window into what the full 10-year survey is going to uncover once it formally gets underway. And this genuinely was just the beginning. Since that initial first-look dataset, Rubin's science team has continued running commissioning and early optimization observations well ahead of the official 10-year survey start, and the numbers have escalated dramatically. By April 2026, the observatory's science team, working with data processing software developed at the University of Washington, had identified more than 11,000 new asteroids from just a month and a half of early-stage observations collected the previous summer, along with roughly 380 newly discovered trans-Neptunian objects, icy bodies orbiting far beyond Neptune, two of which were found on extraordinarily elongated orbits, stretching out to nearly 1,000 times the distance between Earth and the Sun at their farthest point, placing them among the 30 most distant minor planets ever recorded in our solar system. Then, on February 24, 2026, Rubin successfully tested its automated public alert system for the first time, issuing 800,000 individual alerts to the global astronomical community in a single night, flagging new asteroids, exploding supernovae, flaring supermassive black holes, and variable stars, all detected and cataloged automatically as part of a single night's data run, a milestone the observatory has described as one of the final steps before its full legacy survey of space and time formally begins. That escalating pace matters enormously for understanding what 2025 MN45 actually represents. It isn't an isolated fluke discovered through years of dedicated searching. It turned up almost incidentally, buried inside a routine engineering test conducted before Rubin's real mission had even technically started. If a still unexplained physics-defying object like this showed up in just 6 weeks of preliminary test data, the reasonable expectation among researchers is that Rubin's full decade-long survey, scanning the entire visible southern sky repeatedly, night after night, for 10 consecutive years, is going to turn up considerably more objects that don't fit comfortably into existing models, not fewer. So here's where this genuinely leaves us. An asteroid nearly the size of 8 football fields, spinning at a rate that pushes right up against the theoretical strength limit of solid rock itself, discovered not through a dedicated hunt, but almost by accident, buried inside test images captured, while engineers were still making sure a brand new telescope's camera worked correctly. The leading explanation, that it's an unusually rare, solid, monolithic asteroid rather than the loose rubble pile most objects its size turn out to be, remains a genuine hypothesis rather than a confirmed answer. And the scientists who found it are on the record, plainly, saying they don't fully understand how an object like this actually formed or came to exist in this state. That's not manufactured mystery for a video title. That's an actual unresolved question sitting in the peer-reviewed scientific literature right now, discovered by a telescope that hadn't even officially started its real mission yet. If genuinely unresolved discoveries like this, the kind researchers themselves are openly puzzled by, are what you come here for, subscribe and turn on notifications. Because Rubin's full 10-year survey is only just getting started, and if this is what turned up during equipment,